Nice. Okay. Hi everybody. My name is Matthew. I'm going to talk about how people search works at LinkedIn. Just as a show of hands, who here has tried to look up somebody else on LinkedIn before? Oh, great. Okay, you've heard of the product. This is good. So a bit of an outline of what we're going to go through. Quick intro about myself. I'll talk a little bit about search on a high level. After that, we'll spend a lot of time going through the details on how ranking works. If you do not have an ML background, do not worry. I have a quick crash course on the essentials that you'll need to know. And then after that, with any time left over, we'll explore the infrastructure that supports people search ranking. Okay, quick intro into who I am. My name is Matthew, spelled M-A-T-H-E-W. It's just one T. I work on the ranking algorithms for people search at LinkedIn. I've been doing this for a little over 2 years. Before that, I was working at a very small startup working on a type of natural language search, something in the kind of AI assistant space before all of these LLMs came out. I am from a relatively little-known country up north that's kind of cold. You might have heard of it. It's called Canada. All right, so what is search? Let's start with LinkedIn's mission. LinkedIn's mission is to connect the world's professionals to make them more productive and successful. If I can convince you that LinkedIn search helps make this mission happen, then my mission will have been successful. LinkedIn at its core is a social network. It is a community, and the backbone of a community is where members interact with each other. Specifically on LinkedIn, this can happen in a number of different ways. The ways that this is relevant to search is that search drives a number of important actions on LinkedIn. So things like follows, we drive people following each other, connections, people sending connect requests, things like joining groups, and things like sending messages to each other. So based off of this, search enables members to interact with each other, which is key for a social network. Search also serves many verticals. So here is sort of a quick anatomy on how search, on sort of the pieces of the search. So it starts with you, the person doing the search. We call you the searcher. You might type in a query, which is a textual expression of what it is that you want. And then we have different things called verticals. So we don't just surface people in the search results. You might have seen that we show you posts. Sometimes we might show you groups. We might show you other things. Each of these verticals is a type of result that we can show to you. And when you drill down to a specific vertical, the thing that shows up is the document. We're going to be using these terms a lot later on, so hopefully you're comfortable with that. When it comes to other parts of search on a high level, this is an example of what happens when you type in LinkedIn into the search bar and you just hit enter. It'll show you this thing called blended search. Internally, we call this BSERP for blended search results page. It shows you a number of different things. We have this thing called a knowledge card up here, which tries to give you a quick snapshot of maybe the entity that your query is referring to. Underneath that, we got people results over here. This is a cluster full of people profiles that might be affiliated with LinkedIn, which you typed in. Beneath that, we have some posts that might be related to LinkedIn. We also put other recommendation services. So this is from another team where we kind of recommend you companies that you could follow. And sometimes we have custom clusters. You can see over here, these are links to profiles, but specifically they're trying to show you people who might talk about a certain hashtag. So we like to experiment with a little bit of clusters here and there in case you've ever seen them. This is the anatomy of searching for people specifically, and we're going to spend the rest of our time talking about searching for people since it's such a big use case when it comes to LinkedIn. Similar to before, you have it starts with you, the searcher, the person doing the search. You type in a query, and then you see documents populating your search results. In this case here, documents and profiles are pretty synonymous here because all of the results represent a person who could appear in your search results. Another important distinction when it comes to people search is trying to classify the type of search or trying to bucket the type of search so that we can better serve you. A very convenient way of doing this is asking the question, are you looking for a specific person? And there are only two answers to that. You're either looking for a specific person or you're not. In the former case where you are looking for a specific person, this is called a navigational query. This is, colloquially, you might call this LinkedIn stalking. For example, if you were to look me up after this, you might type in the query, Matthew LinkedIn. That's a navigational query. And we understand that as you wanting to navigate to a specific person. On the other hand, if you're not looking for anybody specific, you might just say, oh, I just want to find people associated with LinkedIn. I don't care who the person is. Just show me someone who's good. That is something that we call an exploratory query. So let's talk about how the ranking works. So for those of you that are not familiar with recommendation systems really are simple. First, you get the documents that you think are relevant to what the user is looking for, and then after that, you put the good ones at the top by scoring them. I'm making a big oversimplification here. If you work deeply in the recommendation system space, you can come for me after lunch. So the goal of retrieving the documents is to, we sometimes call this candidate generation. The goal here is to identify every document that could be relevant. On the other hand, when it comes to the scoring and ranking part, we want to make sure that the best documents are scored such that they are put at the top. In some ways, you can think of retrieval as a high recall step, where the cost of omitting a relevant document is high, but if you let in a couple of documents that aren't too relevant, that's okay, because hopefully you could downrank them later. On the other hand, the scoring and the scoring phase and the actual ranking can kind of be thought as a precision step. You want to make sure that the stuff that ends up at the top is truly the things that should be. There's also another notion here where retrieval uses scores, but these scores are statically generated. They're created offline. I'll talk a little bit more about this later. And when it comes to the actual scoring and ranking part, those scores are generated on the fly. So you can think of those as dynamically generated. A quick architecture. So a quick architecture on how the search ranking works end to end. The first thing we do is we generate candidates. This is the retrieval step that I talked about. We go to our search index, do a little magic, which I'll explain in a bit. We get back some documents. I've sort of bolded document C over here to foreshadow that this is going to be the top ranked result. The idea is we get these documents from the search index. We do a little bit of a pre-filtering step. We truncate based off of static rank. Static rank is that static score I was talking about. The reason why we do this pre-filtering step is because later on, the models that we use to rank are going to be deep learning models. And deep learning models are expensive to run. One way to cut costs is to simply score fewer documents. We pass this to our first phase ranker, L1 ranking. And we produce L1 scores over here. We do a similar filtering step, again, because the model that we're about to use downstream is more expensive, and we can cut costs by just not running the model as much. We take the top K, and we pass these documents over to L2. L2, our second phase ranking, is again a more expensive model that focuses on personalization. So we do L2 scoring, get our scores, re-rank them, and then send them to you, who's doing the search. So that was an overview. Now we can talk about the first phase, or the first phase of how our recommendation works, which is the retrieval. So at a glance, you might type in some query that looks like this, maybe Matthew Engineer LinkedIn. At this point, the query is just a string of characters. There's no meaning attached to it. The computer doesn't know anything about what Matthew or Engineer LinkedIn means. So we need to put some meaning to these terms. We do this by producing a tagged query. This is called query tagging. You can see here that Matthew is a first name and Engineer is a title and so on. After we've assigned meaning to this query, we turn it into something called a rewritten query, which is a set of instructions that we tell our search index. It's a set of instructions that tells our search index which documents we would like to return, the conditions that the return documents should meet. So let's focus on this part first. So when it comes to query tagging, we need to take a quick detour down to some classical NLP techniques. There's something that's called named entity recognition. A named entity is a piece of text that generally refers to some kind of person or place or thing. Named entity recognition is an NLP task that tries to identify these named entities in a sentence. So as a concrete example, maybe I've written down this sentence here. Ryan Roslansky is the CEO of LinkedIn, which is headquartered in Sunnyvale, California. An example of a named entity recognizer output might look something like this, where Ryan Roslansky is a person, CEO is a title, LinkedIn is a company, and so on. So when we apply this NLP task to search, this is what we call query tagging. The goal of query tagging is we want to, we're given the query and we want to identify terms or spans of terms into one of the following categories. We want to identify our first name, our last name, company name, school name, and so on. The other thing that occurs under the hood is, at any time that's possible, we want to associate tagged parts of the query to some sort of ID in our knowledge graph. This, if you're wondering why this is important, imagine what happens if you have two people who make two different queries. One person makes a query that contains the term Facebook, but the other person makes a query that contains the term Meta. You and I both know that these refer to the same company, so it would be nice for us to, it would be nice for our search system to be aware of that. The way to do that at LinkedIn is we tag both of these as a company name, and then we associate them both with this company ID in our knowledge graph. So this helps us overcome two different strings that refer to the same object underneath. There's quite a lot going on the slide, so I'll try to unpack this a little bit. But query tagging is important because it helps us with retrieval. Imagine I had a query over here that said Apple software engineer Michael Dell. And I tagged it by saying that Apple's a company name, software engineer is a title, and so on. What we'll find later on when I explain to you how the index works is we store documents divided by the fields that, divided by the values that can occur in different profile fields. So query tagging helps us be more precise with with the documents we extract without sacrificing recall at all. Consider the term, the company name, Apple over here. I can go into my company name index field and I can say, oh, here are the people whose company names are Apple. This helps us be more precise because then maybe there's another part of my query where maybe the person's last name is Apple. Being precise with my query tagging lets me avoid irrelevant documents without much cost. The other part here that makes query tagging important is that it helps us with ranking too. Imagine, consider person 3 over here. You can look in sort of this example up here that person 3 meets all the conditions for our tagged query. Their title is software engineer, their company name is Apple, their last name is Dell, and their first name is Michael. If we tell this to the model and say that the query matched the document on these different fields, it's generally a pretty useful ranking signal as to how relevant a document is. So query tagging helps with ranking. Okay, now that we have assigned some meaning to our query, we want to turn this into a set of instructions for our search index. This is called query rewriting, and it produces a very imaginative name called the rewritten query. So, has anybody, who here is familiar with the idea of a search index? Okay, cool. For any of you who didn't put up your hand, that's okay. Imagine you go to the back of a textbook and you look up terms in what's called the index. What you'll see is a term and then a list of pages that contain that term. This is pretty similar to how a search index works. Here you have some kind of term, and then you have a list of documents that contain that term. Now, the great part about people's search here is that everybody's profiles are structured in the same way. My profile contains the same structure as your profile. We have to fill in, first names, last names, company names, and all that kind of stuff. Which means that we can take this indexing one step further, and we can associate not just a term, but the field name of the profile that contained that term to the list of documents. Enough with the abstract. Here's something slightly less abstract. For example, I might have an inverted index that says, okay, for all the, give me all the documents whose first name is Matthew. Then you got documents 1, 2, 4, and 5, and so on. And similarly, we can look at documents for whom current title is engineer, and then you get the then you get the documents there. So we want to split our inverted index by profile fields. The rewritten query will be kind of looking at this as a way to get the documents. So when constructing this rewritten query, a few things about it. It's a very large Boolean string that that specifies the conditions that return documents need to follow. Just like any other Boolean operator, Boolean strings, you have your kind of required clauses, optional clauses, negation clauses. Another thing we do is we also map the query tags that we were talking about before to the actual inverted index fields. So here are some examples of our inverted index fields. You might recognize these as things that you might have had to fill out in your profile. We've got first names, last names. Connections are not things that you explicitly fill out, but they are part of your profile, and we consider that important. We have your current company, past company, your profile headline, and some other things. We also have these mysterious looking T fields over here, which represent groups of profile fields that we may want to match on. This is something we use when we care about matching on a group of profile fields, mainly for to help with rewriting. We have a few tricks to optimize recall at the bottom over here, so let's go through them. This is an example, a somewhat condensed one, of a rewritten query. You can see that there's some stuff on the left over here that's related to first name Christopher. So what's that? We have some stuff related to being an engineer. What's this all about? So let's start with this. Imagine you met somebody at this conference. Their name is Chris, but they didn't take the time to spell it out for you because that's usually not what people do. You might go into LinkedIn afterwards and you might type in CHRIS. In theory, because LinkedIn is a professional platform, people might represent themselves with the expanded version of their first name. Perhaps they didn't write Chris on their profile, they might have written Christopher. It would be unfortunate for you to type in Chris into LinkedIn search and not get back the Christopher that you had met. We overcome this lexical gap with something called query expansion. You can think of this as sort of a nickname mapping, where we have Chris, and then underneath, whenever we see Chris, we add Christopher to the rewritten query. You might get Matt to Matthew, and things like that. So that's one example of how we do query expansion for names. The other thing is, and again, if you don't introduce yourself by asking people to spell their names, they might have spelled their name differently from the first spelling that comes to your mind. Perhaps you met this Chris who spelled their name as K-R-I-S. Again, it would be unfortunate for us to miss that profile simply because you chose a different spelling. So we do something that's called name clusters, where we take a bunch of different names that occur in LinkedIn, and we cluster them. We group different names together based off of lexical similarity. You can see KRIS, CHRIS, they all belong to the same cluster, and we assign a cluster ID, which helps us with rewriting. The other thing that we do over here is ID-based retrieval. So this helps, again, to overcome lexical gaps. Perhaps one person typed in engineer in this spelling, somebody else typed engineer with in a different language. We would like to associate both of those with the same ID so that we can retrieve, so that we can retrieve better. This also helps if you have two different ways of expressing similar jobs. So historically, LinkedIn used to call their ML engineers data mining engineers, And again, yeah, it would be nice to associate both of these with the same ID so that we're not as sensitive to exact spellings. All right, now that we're done with the query rewriting part, let's go into the actual retrieval step. We have all the pieces that we need. I told you about this already. Here is the rewritten query. As sort of a spoiler alert, documents 2 and 4 come back as a result of this retrieval. That's because they meet conditions like these, conditions like the current title being engineer, headline containing engineer, as well as current positions containing LinkedIn. So when you have documents that meet all of those conditions, then you have your set of returned or retrieved documents over here. In this example, it's kind of contrived because I only gave you 2 documents, but what happens if we have too many documents? This alludes to what I was saying earlier about our static scores during retrieval. The idea here is we don't want to retrieve too many documents because these documents get passed to our deep learning rankers, and it would be nice to save costs because deep learning models are expensive to run. We can save costs by simply running the model fewer times, and we can do this, and this helps in retrieval by filtering based off of a static rank cutoff. So static rank is a model that tries to predict the popularity of a profile. Under the hood, it's related to trying to predict the number of views that it'll get in some future time period. And by doing that, this determines the retrieval order for the documents. Okay, so putting it all together, we have our query, we tag it and assign meaning. Then from there, we assemble a set of instructions for our search index to give back to us, and then we retrieve the documents. Congratulations, you made it through the first half. We are 27 minutes to lunch. All right. Next, I'm going to go over the basics of ranking models. If you are an expert in ML, you can, you don't have to pay attention to this. I might oversimplify some things, but again, you can come for me once lunch starts. For anybody else who has not had much exposure or need a refresher, we can dive in. So, what is a machine learning model? Specifically for supervised machine learning tries to predict an outcome based off of some object that you give it. In sort of a simple relevant example that might work for our domain is, let's say you're given a profile, you want to predict whether or not it's going to get a click. The way that this prediction happens is that the model computes some kind of probability, and the computation of this probability is governed by something called weights. Which we learned, which is where machine learning comes from. When it comes to ranking models, this is quite similar. The distinction here is that the end result that we care about is the order in which things are ranked. So in a sense, the scores are sort of the scores that we output, the probabilities that we output, are something of a means to an end. And this is something that is a little bit important once we start talking about learning to rank. So over here, if I have a search result, the thing that appeared at the top, you would say has the highest score. Okay, so a toy example of a ranking model using my favorite model, logistic regression. This tries to model the probability of a click given a profile, and it takes in one feature, which is X, the number of common connections. The weights here govern how the computation works. Here we're multiplying some weight to common connections plus adding a bias, and then we throw a nonlinearity on top of that. If that is too difficult for you to plot in your head, don't worry, I've done it for you. So this takes some real valued number and squeezes it between 0 and 1 so that it kind of looks like a probability. If this sort of DAG structure looks like a composable unit to you, well, yes, you can compose it and expand it this way, and you can expand it this way, and if you had that idea, congratulations, you just invented deep learning. Also, this took me a long time to animate. All right, so when it comes to training these weights, this table that I have on the right here is pretty much what our training data looks like. The features might look a little bit different, and K might be, K it takes on a range of different numbers, but under the hood, when we train our models, the training data looks like this. So there are a couple of things here. I'll talk a little bit about the features and the labels, but the way to read this is that we have is that every single row corresponds to who made the search, what the search query was, which document we're considering, and then the outcome of that document, which is whether or not it got clicked. So over here, searcher 100 searches for LinkedIn and then clicks on profile 1. We know the click happened because that's where the label is. And then over here, searcher 201 searches for accountant and clicks on profiles 3 and 5. So this is what the training data looks like under the hood. So anytime I talk about training a model, try to remember this. I'll have a picture of this in the corner in case you can't remember what it looks like. Okay, with features. Remember how we were talking about the anatomy of search? There are 3 actors in this play. There is you, the searcher, there is the query that you typed in, and then there's the document that we're trying to score. There are interactions between all 3 of these actors, and all of these provide rich signals for whether or not something is relevant. We have the query document match. Did the which parts of the profile did your query match against? We have things that you and the profile have in common. So these are things like mutual connections and possibly like physical distance or like geolocation differences. Sometimes we have features that are related to the document itself, and other times we have features that are related to just the query itself. So there are many different places that we can get our feature information from. On the other hand, for labels, labels are supposed to measure how relevant a document is. We approximate this by whether or not you clicked something. In this case, we try to make these clicks meaningful. We try to look for the meaningful clicks. So did you follow them? Did you connect with them, message them? Or maybe you clicked on their profile and read for a certain amount of time. If you did any of these types of things, we would consider that to be you finding a relevant document, which is something we'd want to tell the model about. So now that we have the features and now that we have the labels, how do we train these weights? First, you pick a set of weights. Then you compute something that's called the loss, which is a measure of how poorly you're doing on your training data set. You compute something called the gradient here, which somewhat tells you which direction to adjust your weights to make it just slightly better. You rinse and repeat, and either until you found something that is good enough or you've gone through a certain number of iterations, then you stop the training process. Again, big oversimplification. You can come find me at the beginning of lunch. That was the 1D version. The 2D version might look something like this. Again, these are very convex, playing nicely loss functions. And for any of you who have trouble sleeping, here's a math equation. Here's your current weights. Here's the gradient. Sometimes you scale this by a learning rate. Rinse and repeat, you get your new weights. So the question here, the question that kind of remains is what's the loss function and what's the gradient? As a recap, we care about the best order for our documents. So here's a trick question. Which of these ranking scores is better? The trick answer is who cares? Because these are a means to an end. We just care about the order of the documents. And this is important for reasons I'll explain in a sec. What's a good loss function for ranking? Well, the answer lies in something called learning to rank. I'll quickly cover pointwise, pairwise, and listwise. And hopefully you'll be able to take something away from that. So just as a recap of where we've gotten to so far, I've explained to you a little bit about how ML works. We've talked about the features, we've talked about the labels. I've sort of talked about the weights and how we adjust the weights here and there. But the remaining piece of this equation is how we even adjust those weights. And that lies a lot in this loss function. So easiest example is the easiest method is pointwise learning to rank. You're essentially treating this as a regular supervised learning problem, where for every document you try to predict whether or not you got a click. So your model would iterate over literally every row of the data set. And this is simple. I mean, if you think about it, if something is more likely to be clicked, then it's probably more relevant, which means that you should put it closer to the top. But the problem here is we don't really care about this point-wise learning to rank doesn't really consider the order of the documents. And again, like I mentioned before, nobody cares about the actual scores that you have here. People just care about the order in which the documents are ranked. So this is flawed because it doesn't contain information about the order of the documents. It doesn't tell us anything here about how profile 5 is better than profile 7. So what do? We can take this a step further. We can go pairwise learning to rank. This compares pairs of documents, and the model tries to predict which document is better than the other. So in a sense, so over here it would try to predict that profile 1 is more relevant than profile 2 for this search. Profile 3 is better than profile 5, and profile 3 being better than profile 7. So this is a slight improvement because it kind of compares documents now and sort of implicitly defines an order. But what if we did this for all of the documents that we're ranking for a given query? As a warning here, there's some math.
As usual.
As usual. What's the best way to explain this? So we have our ranking scores. Because this gets very mathematical, the people who wrote so the one thing I should say is that listwise, there are a range of listwise methods. I just picked listnet because this is the one I understood the best. But because this gets more technical, it ends up being more convenient to create actual probabilities from the scores that the model is generating. So you can forget you don't have to worry too much about the stuff over here, but essentially for every document, we're trying to associate a probability with it because this is important later on. So we have some document score that the model outputted, and we convert this into a probability. Put in a slightly more general and painful format, we have the probabilities for all of for each document for a given search. And once you have the documents here, you can kind of plug this into once you have the probabilities here, it's somewhat smooth sailing because you can apply this loss function called the cross entropy loss, which is something that is commonly used across machine learning. And I won't prove it here, but this is the gradient that we're talking about. Again, you don't need to be intimidated by the symbols here. All we need to know is the loss, which tells you how poorly you're doing on your data, and then the gradient, which is an expression that helps you adjust your weights for the next iteration. So now that we have this, we can now train our models. All right, congratulations. Yeah, you made it there. You got 17 minutes until lunch is ready. So this is what I assume most people came here to learn about. So this is what you're going to get. This is the details of the ranking models. So as sort of what I mentioned before, L1, which is our first phase ranking, is one that focuses on how the query matches the document. The input is thousands of documents, and the output is hundreds of documents. We sort of talked about the retrieval already. We produce a score using the ranking model I'm about to show you, and then we take the top K, which gets passed to the second phase ranking. Okay, so a quick dive into how we represent our features. I talked a little bit about the numerical part where we have, say, the number of common connections. You can put that into a vector, give it to the model, then that part is relatively easy. But I didn't talk much about how we represent text. A big shout out to the previous presenter who talked about embeddings for text. Because of that, there's a little bit more that we can go off of. It turns out you can use convolutional neural nets to create an embedding for text. And this is useful for us because associating a vector for any given piece of text where similar pieces of text are closer together in that vector space makes it very powerful for us to represent when it comes to the ranking model. So on the big picture over here, there's quite a lot to unpack here. But the most important thing that you need to know about right now is this guy in blue over here. This is our feature vector. And remember, kind of like what I said before, if you have the feature vector and you have the weights of the model, then you can run your prediction. But why is part of this shaded darker than the other? So there are two types of features over here. There's something called deep features, which I'll talk about in a sec, and then something else called wide features. So what does this refer to? Broadly, deep features refer to features that are generated by sort of the more deep learning side of our model. You can see over here that we take in our query as one of our inputs. We want to pass this through a CNN, and it'll generate an embedding for us. But remember, we also have other parts of other pieces of text that we might want to consider as well. So when it comes to the document profile, we might care about things like headline or title or skills, because these are all predictive as to whether or not a document is relevant. So we want to pass each of these through a CNN as well, and then we will create an embedding for each of them. But instead of putting these embeddings directly into the model, we add another trick, which is, because again, we care about how the query we care about how related the query is to text on the profile. So so it makes sense to compare them directly. So over here, we compare the embedding for the query and the embedding for the headline. And you can do something like a cosine similarity, and that becomes one entry in our deep features vector. You can rinse and repeat. You can do the same thing for fields like titles, get the cosine similarity with the query, and then that's another deep feature, all the way down to stuff like skills, and that becomes an entry in the feature vector. So that's the deep features. When it comes to wide features, these are just the numerical features that you might have thought about. So maybe over here, the number of mutual connections is one such feature. This is an example of something that goes into the wide features. Once we have this feature vector, we pass this through our sort of a standard feed-forward network, and then out comes the score. So that is L1 ranking in a nutshell. The good news here is that if you made it through this slide without falling asleep, L2 ranking is similar. A few differences. Instead of using a convolutional neural net, L2 ranking uses a BERT model, which is a little bit more expensive, which is why we try to pre-filter a little bit before getting there. The other thing too is we use we also look at the searcher's profile, which I'm about to show you. So there's a lot to unpack here, but this is the same slide. This is pretty much the same slide that I had before, except turned like this way. We get an embedding for the query over here, same as before. Only difference is that we now use a BERT model for it. We have embeddings for the document, kind of like we said before. And just as promised, we have embeddings for the searcher's profile too. This is where some of the personalization comes in. We do our kind of cosine similarity to get the deep features, similar to what we said before. And then this part over here are the wide features, similar to what we had before. We pass this through a hidden layer, and out comes the target score. Now, one other trick that we do is that this green part and this purple part over here, they both run online in real time. But the embeddings for the searcher and the document, it turns out you can pre-compute those and then cache them and then retrieve them online. So that saves a lot of model computation. In terms of why we care about L2 ranking, like I mentioned before, L2 ranking is a personalization layer. So on the left side, I've searched for LinkedIn, and I have L2 ranking switched on. It shows me, I had to blur out their faces, but you'll just have to take my word for this, that these are coworkers that I haven't connected with yet on LinkedIn. So it's personalized in the sense that they're people that I work with. On the other hand, if I switch off L2 ranking and only use L1, then I get sort of generic, kind of generally popular results. That's how we get Ryan Roslansky, the CEO, at the top, because he's an example of somebody who's kind of universally popular on LinkedIn. So if you are interested more in how this works, the good news is that this library is open source. So you can try this yourself on this link over here, dtext. And like I mentioned before, we have query embeddings. We have some other we have the query embeddings. We have these text interactions and these other wide and sparse features that come with it. All right, congratulations, you made it through the rankings. So give yourself a pat on the back. With the remaining time that we have, I think we have about 10 minutes. So I'll go a little bit into the infra, and then we can take some questions. Sound good? Yes. All right. So we have our own ML ops stack at LinkedIn that is called ProML, stands for Productive Machine Learning. This includes tooling for things like offline feature management for training, online feature management for inference, as well as things for training models, as well as productionizing them. This is very important. The standardization is very important at LinkedIn because tool standardization is somewhat of an accelerant and helps us work at scale. For example, I could go to another team tomorrow, not that I will, I could go to another team tomorrow and look at their code, and the tools are going to be relatively the same. And where the main part I'd have to ramp up on would be the domain that they're working in. So this is something that helps a lot. There's a little bit, and in terms of our actual search infrastructure, it looks something like this. The query comes in, we have this thing called the federator over here that fans out to a number of different verticals. The people search vertical is one vertical of its own, and everything and a big part of what I talked about happens here. So all of the retrieval and L1 ranking happens within one shard. If you're unfamiliar with the sharding concept, because LinkedIn has 930 million members, it doesn't make sense to do computations for all 930 million members on a single machine, so we split it onto a number of machines. This means that the retrieval and L1 ranking happen in parallel across the shards. We merge those results up in the broker. And then after that, we pass it over to the federator that does L2 ranking. So yeah, in summary, people search is simple. It's just, it's simple. First you get the profiles, and then you put the good ones at the top, right? Recommendation systems are simple. The second thing I'd like you to know is that the query is just a string of letters. The computer doesn't know anything about it. It's up to you to assign meaning to it, whether or not it's tagging queries, getting IDs, and that's where the query rewriting happens. And one of the most underrated tips for running deep learning models at scale cheaply is to just not run it too many times. There's no secret there. So hopefully you had something to take away from it. So thank you very much.
One question: how do you define static scores in a way that's relevant for every search context?
That's a good question. I think the key. So I will preface this by saying that I did not make the static rank model myself. So it was actually done by one of my coworkers. The idea behind that is to use features that are, like you said, relevant for every search context. So you wouldn't want to make it too specialized, and we also don't lean too heavily on the static rank as a kind of mission critical thing. The other thing that often helps is this is a continuously running pipeline. It's not something we run once every quarter and then let it go stale. So there's a couple little tricks there.
Hey.
Hello.
Hey, so question about your attribution that you were just talking about when you guys take into account clicks, right? Is that the only label you guys care about? And then if a certain person was impressed on multiple search pages, do you care about the last one, all of them, without revealing any NDA or stuff like that?
So when you say a person was impressed, if the person
on the search page, for example, like do you label all of those? Like say I was searching a bunch of times, I was searching Matthew a bunch of times, and then I clicked on the last time I searched it, I clicked on your profile.
It's
right.
A refinement. It's kind of like a query refinement.
Oh, you mean like successive searches in a single session?
Yeah. And then I clicked on your profile on my last search. Do you care about all of those? Do you label all of those as a click, or do you just label the last one?
I think all of those are, like, basically if you are on a page and then you make a click, that now becomes part of the training data. There are some optimizations that can be done by like considering successive searches, but we haven't really found much success in that yet.
Awesome.
Yeah.
Thanks.
Yeah.
I have a question about the cost. So as it's because we're in a very volatile marketplace, so in case I bought a LinkedIn Premium, adding a lot of new friends, so my document will change a lot. So my question is, how often do you run the model to update the documents for the label or the L1, L2? And the follow-up question is, have you guys thought about using heuristic to simplify the model to make it run faster and cheaper?
Yeah, so in terms of your first question, the frequency with which we run the model, we haven't quite gotten to the place yet where we're auto-training it every single day. The problem with auto-training is that your label distribution can change. I use the click label as a simple example, but there's quite a lot that goes into crafting what this label is. And you get into these cycles where if you have a certain ranking model that does a certain ranking treatment, that can affect what the label distribution looks like in the future. So auto-training is somewhat out of the question. Yeah, it's done somewhat, but model training is done somewhat occasionally. In terms of your second question, can you remind me what that was again?
Heuristics.
Oh yeah, heuristics. Yeah, so there are definitely places to do that. I think I talked a little bit about how turning L2 ranking off makes the results less personalized, but in certain cases, L2 ranking doesn't really give the ranking for certain queries that you actually want. So sometimes we will turn L2 ranking off based off of some condition, and then that helps optimize the results a little bit more.
Matthew, but the other thing, like when you add a connection, it goes into the index under connection. So the retrieval phase, the model doesn't get updated. It's just a
That's correct.
match.
Yeah. So one.
Real time.
Yeah, so in terms of changes to your social graph, those get updated in the index, and the index contains the index will contain information about your connections, and then that fuels the values of the features that eventually get used for ranking. So even if the model itself is not updated every single day, the features are updated regularly because they depend on what you do in LinkedIn. So those feature values will keep up.
Yeah, I have a question about the ambiguities in tagging phase.
Yeah.
Maybe I missed some details.
Mhm.
But I think you have a good example, right? Apple can be either a name or a company name.
Yeah.
So when I put Apple there, do you actually have like deterministically can tell in the tagging phase that this is a company name, or you just assume that it could be both and you consider both situations?
So I think there are certainly edge cases, and like this happens. This actually there are certainly edge cases where the query tagger might get a wrong answer. Actually, I was looking up a friend who was working at OpenAI, and I didn't capitalize anything. It just said OpenAI, and it tagged that as a last name, right? So usually when that happens, we get complaints from members. That's usually the first thing. But as far as ambiguities go, I didn't quite go into the details of how query tagging works, but it does try to look at the surrounding terms, right? So based off where the term occurs in the query, that also gives you a little bit of signal and could disambiguate cases like what you described.
We can probably do 2 more questions.
Yeah, I think. Oh yeah.
Thank you. So one question is around your architecture. How do you handle latency? Do you have a budget for it? Do you just track it and make sure that it doesn't go over some SLA that you have? Because I imagine that people will give up if it takes too long to give the right results.
Yeah. So so for each of the models that we have, this is something that we work closely with Infra on. So the people, so this architecture over here, the people who work on both the federator and the broker and searcher, they have dashboards that track, the average amount of time it takes for these models to score. Sometimes we also look at stuff like memory consumption, and if those go above a certain threshold, then it's something that we take a look at. So that's definitely a big piece.
Do you treat every searcher equally? Like if there's someone who is very curious and has a lot of time on their hands,
Yeah.
do their weights matter less or more than, like, for example, a recruiter or a headhunter?
Yeah, so this is a very good question, and I think this is where we spend the bulk of our time. So let's say you had somebody, we actually, internally we call them power users. So if you had somebody who searches a ton, let's say like thousands of times a day. I'm not even sure if I haven't done the math on whether that's physically possible. You would expect if we randomly sampled searches that this power user would appear several times. So that is not a good thing for training data. So this is an example of something we try to prune out. And making sure that there isn't too much over representation is definitely making sure that that doesn't happen is the result of like data analysis, a lot of data analysis, and interrogating your training data. So it's something we work very hard to prevent, because given a limited budget of training data, if a certain type of user, maybe the power users are overrepresented, it also means that other users are underrepresented, and there are somewhat diminishing returns on how many times you can appear in a data set and have a good quality search experience. So great question, yeah. I'll be around, after this, so if you want to chat some more, you know what I look like.